Hey BC Cal students, this video covers alternating series. All right, so let's talk about alternating series. An alternating series is a series whose terms are alternately positive and negative. So if we had like 1 minus a half plus a third minus a fourth, which is really just -1 to some exponent over 1 over n, times 1 over n, this is an alternating series because we start positive, negative, positive, negative. And then the second example, we have negative, positive, negative, positive. So how do we determine if an alternating series is convergent or divergent? So we can't use P series because the terms don't all have the same sign, and we can't use geometric series because it's not the function, just the sequence just doesn't have to be a geometric sequence. And we also can't really use the nth term test for divergence because there are too many different options that can come up for an alternating series. So the convergence of an alternating series is based on 3 criteria. The first one is always going to be really apparent. The terms of the series alternate between positive and negative or negative and positive. Again, that's going to be really straightforward. You can just look at the series and tell. If you ever need to know, if you look at the exponent, as long as the exponent is linear plus a number, so there's no multiple. If it's n plus 1 or n and it's -1 to that power, it's always going to be alternating. Now, if you get into like 2n plus 1 or just 2n, then it's either always going to be negative or always going to be positive, because 2n is going to be even, 2n plus 1 is going to be odd, or 2n minus 1 is going to be odd. So the second criteria is that the terms decrease in magnitude. And you can generally determine this by just looking at the sequence. And if it helps, write down a couple of terms to see what happens. But it's pretty clear that if you ignore the sign, then 1 is greater than a half is greater than a third is greater than a fourth would be greater than a fifth, and so forth. That's what we mean by decrease in magnitude. The terms, ignoring sign, they get smaller. And the third and the most crucial one is that the limit of the sequence that generates the series has to be 0. So in the previous video, we talked about the nth term test for divergence, where we said that if the limit of the sequence was not 0, then the series was divergent. That's going to be crucial for the alternating series. So if an alternating series is absolutely convergent, that means that in absolute value, the series converges. That means that if you made all of the terms positive, would the series still converge? If the answer is yes, that's what we call absolutely convergent. And if you take away the negatives, make all the terms positive, and then the series does not converge, then we call that conditionally convergent. So the tests for this are pretty straightforward. You just have to answer these 3 questions. Primarily, you really just need to answer the third one. You need to check the third one. If the limit of the sequence is 0, then you're looking at least a conditionally convergent alternating series. And then when you check for absolute value, you possibly have an absolutely convergent one. So for example 1, we have, and again, for all of these, I left out my n equals 1. I do not know what Mr. Martin is thinking. So we have this series n equals 1 to infinity of -1 to the n plus 1 times n over 3n plus 2. So if it helps, let's write out a couple of these terms. So when n is 1, we're going to have -1 squared times 1 over 5. And then when n is 2, you're going to have -1 cubed, which is going to be -1. So we're going to have minus 2 over 8. Then we're going to have plus 3 over 11 minus 4 over 14 plus so forth. So the terms of the series alternate in sign. So we're just gonna write 1, 2, and 3 and check them off. So 1, they alternate in sign. 1/5 is 1/5 less than 2/8. Well, that's 1/4, and that's 0.2. So 3 over, we can check this on a calculator pretty quickly. And so you know what? Let's go without a calculator. So say you can't answer 2 without because you don't have a calculator. 3 is always going to provide the answer to 2. So whatever you get, like if you get a sequence of 0, if you get a limit of 0, then it's going to mean that the terms ultimately decrease in magnitude. If you get a limit that's not 0, it means that the terms do not decrease in magnitude. So let's check 3. We need to look at the limit when n approaches infinity of n over 3n plus 2. And remember, for rational functions, the limit is going to, if the degree of the numerator equals the degree of the denominator, the limit is the ratio of the leading coefficients. So this limit is 1/3, which is not equal to 0. So this alternating series is divergent. So what that also means is that for 2, we can say because the limit of the sequence is 1/3, the terms do not decrease in magnitude. So again, if you're checking this, and all the time when you do these things on the AP exam, you will not have the aid of a calculator. So 1 is always going to be easy to check. 2, you can do by inspection. But if you feel like you don't know the answer reasonably, skip to 3, find the limit. And if you get 0, it means that 2 has to decrease in magnitude. Or if you get some limit that's not 0, it means that they don't decrease in magnitude. Not that they get larger, that they just don't decrease. For example, 2, we have -1 to the n over n cubed. If we list the first handful of terms, we would get, so we'll get -1, then we'll get plus 2 over 8 minus 3 over, just plus 1/8 minus 1/27 plus 1 over 64 minus 1 over 125 and so forth. So again, if we're checking our criteria, 1, do they alternate in sign? Yes. 2, do the terms get smaller? Well, clearly they do, because you have 1 and -1 divided by a progressively larger number. So 2, they do decrease in magnitude. And 3 is the limit of the sequence that generates the series equal to 0. So the limit as n approaches infinity of 1 over n cubed. Now again, for the limit, we don't care about the -1. We care about what's in the numerator when the -1 is not present. So this limit equals 0 because 1 divided by a very large number cubed is going to be almost 0. So we would say the series from n equals 1 to infinity, -1 to the n over n cubed converges by the alternating series test. So we know the series converges by the alternating series test. Now, a follow-up is this series absolutely convergent or conditionally convergent? And so the test for absolute convergence. So we need to look at the series from n equals 1 to infinity of this series without the -1, which is just going to give us 1 over n cubed. So you think about what happens for a moment and jump back in. So we should know from the P series that this is convergent because P equals 3, which is greater than 1. So this series is not just convergent, it's absolutely convergent. So absolutely convergent by alternating series test. and P series. So in this case, we know this sequence is absolutely convergent because in absolute value, we get a P series 1 over n cubed, and that's convergent. And we already knew that it was convergent by the alternating series test. So it's absolutely convergent by the alternating series test and P series. For example 2, we have, not example 2, example 3, we have -1 to the n plus 1 over 2 to the n. So we won't go through, well, actually, let's list out a couple of terms. We would have, so if n is 1, we're going to have a positive 1 in the numerator. So we're going to have 1/2 minus 1/4 plus 1/8 minus 1/16 plus so forth. So the next term would be 1 over 32, -1 over 64, +1 over 128, and so forth. So if we're checking, 1, the terms alternate in sign, 2, the terms decrease in magnitude clearly, and 3, the limit, so let's check this, the limit as n approaches infinity of 1 over 2 to the n. Where clearly if you divide 1 by 2 to a progressively larger number, you're going to get 0. So this limit is 0. So right now we know it is convergent by the alternating series test, but now we can check for absolute convergence. So for absolute convergence, we need to look at the series from n equals 1 to infinity of just 1 over 2 to the n. Now remember, this looks like it can be rewritten as the series from n equals 1 to infinity of 1 over 2 to the n power. And do you remember what kind of series this is? So this is a geometric series where this is going to be convergent because r equals 1/2. Remember, geometric series are convergent as long as the common ratio is less than 1. So we end up with another absolutely convergent series. Now in this case, it's absolutely convergent because alternating series test passes, and then the test for absolute convergence, which gave us a geometric series, checked out. So absolutely convergent, and we're going to put geometric series. Now for this one, we could actually find the sum if we wanted to, but we're not going to do that. For example 4, we have -1 to the n plus 1 over n. If we list out a bunch of terms, we're going to have 1 minus 1/2 plus 1/3 minus 1/4 plus so forth. So 1, do they decrease in do they alternate signs? Yes. 2, do the terms decrease in magnitude? Yes. And 3, is the limit as n approaches infinity of 1 over n equal to 0? The answer is yes, because you have 1 divided by a very large number, which is going to be 0. Now this is just literally the definition of an alternating series. So right now we have at least convergent by the alternating series, which is going to mean at least conditionally convergent. So now our test for absolute convergence, so we're going to put absolute convergence. I guess we'll write a question mark. So now we need to look at the series from n equals 1 to infinity of just, ignore the -1, so we're just going to have 1 over n. This is going to be divergent because p equals 1. So remember, this is the harmonic series. And for the harmonic series, it's going to be divergent when p equals 1. So in this case, we would say conditionally convergent. For example 5, we have the series from n equals 1 to infinity of -1 to the n over the cube root of n. So if we list out the first couple of terms, we'd have -1 plus 1 over the cube root of 2 minus 1 over the cube root of 3 plus 1 over the cube root of 4 plus. So for 1, do they alternate in sign? Yes. 2, do they get progressively smaller? Yes. So imagine you get out to n equals 8. That would be 1/2 because the cube root of 8 is 2, so you get a half. So we'll even put that in. So 1 over the cube root of 8. So -1. So if you ignore the signs, 1 is less. 1 is greater than a half. Which, if we go out to 27, then you're gonna have 1 over the cube root of 27, which is a third, and that's less than a half, which is less than 1. So ultimately, these decrease in magnitude. And then 3 is the limit when n approaches infinity of 1 over n to the 1/3 equal to 0. The answer to that is also yes, because you're still dividing 1 by a progressively larger number. As n gets bigger, the cube root of n is also going to get larger than the previous terms. So again, we have at least a conditionally convergent alternating series. So the test for absolute convergence is going to give us the series from n equals 1 to infinity of 1 over n to the 1/3. So not equals, but this is going to be divergent because p equals 1/3, which is less than or equal to 1. So by the p series, this time we're going to end up with a series that is only, I ran out of room, so we're going to put conditionally convergent. Conditionally convergent. Alternating series test checks out. The test for absolute convergence does not work, so we end up with conditionally convergent. And finally, we have example 6, where we have -1 to the n plus 1 over 5n minus 7. Times 5n minus 7 over 3n plus 2. N equals 1. So let's see what happens when we find the first few terms of this series. If n is 1, this is going to be a positive 1, and we're going to have 5 minus 7, which is -2 over 3n plus 2. That's going to give us 5. And then if n is 2, you're going to have -1 cubed, which is going to be a -1. And then 10 minus 7 is going to be 3. So minus 3 over 8. And then if n is 3, that's going to be an even number. So we're going to have 15 minus 7 is 8 over 11. If n is 4, we're going to have a negative times 20 minus 17 is -13. Well, -1 times that's going to be -13 over 14 and plus. So despite the first two terms having the same sign, ultimately these terms alternate in sign. So 1 checks out. 2, do they decrease in magnitude? Well, -2/5 is that's 0.4. This is 0.375. That 8 over 11 is, I don't know what it is as a decimal, like 0.72, I think. Let's find out. Yeah. So 3. So again, if you can't really determine 2, jump down to 3. And so then we need to look at the limit as n approaches infinity. Ignore the -1. So 5n minus 7 over 3n plus 2. Now remember, for a rational function for which the degree of the numerator equals the degree of the denominator, the limit is going to be the ratio of the leading coefficients. So our limit is 5/3, which is not 0. So these terms do not decrease in magnitude. So in this case, this we're just gonna call this an, so we don't have to write the entire thing. So we would say the series from n equals 1 to infinity of an fails the alternating series test. You don't have to write why. Like showing your work is enough proof. So the limit is not 0. Just any of these, if any of these do not check out, then the series fails the alternating series test. So to recap, an alternating series is a series in which the terms ultimately alternate between positive and negative. Ignore the first handful of terms if they don't alternate signs, but ultimately if they do, it's going to be at least an alternating series. And then the terms have to decrease in magnitude and the limit of the sequence has to be 0. If that's true, these three conditions imply at least conditional convergence. But then if you check for absolute convergence, now for absolute convergence, you're going to be using all the other tests that we know. So far we know geometric series, we know P series, and we know nth term test. Now remember, the nth term test is just for divergence, not necessarily convergence. So in the next video, we're going to talk about the ratio test. And after we do the ratio test, we may go back and do the limit comparison test. Even though those are not testable on this year's AP exam, I think it's still good for you to know if you're going to be taking calculus in college. So we may or may not include those those series tests in additional videos. All right, take care of yourself, guys. See you later.